Good afternoon. I'm Kiran Venugopal. I'm here to present the work on the analysis of millimeter wave network wearables in crowded environment. This is a joint work with my advisor Robert Heath at UT Austin and Professor Matt Valenti from West Virginia University. So we are going to talk here about the wearable communication network, which we define as the network formed by several communicating devices attached on and around the user body. So this could be the devices shown over there in the figure, with the smartphone acting as a coordination hub for this network. So from an architecture point of view, network architecture point of view, this is similar to the body area network as defined in the IEEE 802.15.6. But then we also include devices that has high data rates, more than like 1 gigabits per second, and also low-end gadgets present in this wearable network. And we associate such wearable communication network with each user. So each user has a communication network attached to him. Now the devices of this wearable network, as we saw, could be, it can be a whole gamut of devices. It could be low-rate devices like the fitness monitors, wherein the battery life and power consumption are the main constraints. We could also have high data rate infotainment devices like the smart glasses shown there, for which the quality of service requirements are more stringent. So they basically need low latency, high data rates like maybe greater than 5 gigabits per second, wherein the power consumption is usually a lesser concern. The challenge here is when we look at how the system performs when a user with his wearable communication network moves into a crowded environment. So each user has communicating networks which interfere with this reference user that's shown here. So the typical crowd densities that we consider are 1 or 2 users per square meter on an average. And if you're considering communication at less than 3 gigahertz and coordinating between these networks in order to avoid interference, what we see is that at these high densities, the overheads are going to be that huge, and getting high-end applications running is going to be challenging, given that the bandwidth available is very low for sub 3 gigahertz frequencies. So supporting high data rates in crowded environment is challenging. So this is where the millimeter wave band comes in. So you have large bandwidths in 60 gigahertz, around the 60 gigahertz carrier. So we have several gigahertz of bandwidth itself for worldwide operation. And most importantly, the property of the signals, these frequencies, is that they don't penetrate well through human bodies or objects. So the signal transmitted from your network, from your device, does not penetrate to, maybe they penetrate to your nearby neighbors, but not to a faraway person, even if the density is high. So possibly you could reuse the spectrum more efficiently. Also, you can use compact antennas for reducing interference, and which means that you are channeling your energy, and even a small fraction of nearby users are affected by you, not the entire set of people around you. So what this means is that possibly if we use millimeter wave, we may not require coordination across the users to address the interference issue that we saw earlier. So some of the prior work, there has been study on characterizing interference in adjacent wireless body area networks. So some of them have been measurement-based studies. There are also analytic models mostly for sub 3 gigahertz bands. As for millimeter wave, stochastic geometry has been used for modeling interference. That has mostly been for cellular systems in which the blockage processors are the, buildings are the blockage source, and they are usually independent of the locations of the interferers. There has also been studies on performance analysis for finite networks, but then those do not include directional antennas or blockages. The contributions of our work is to develop a tractable model for millimeter wave wearable networks to show that high data rates can be supported even in a dense crowd. So using this model, we derive spatially averaged performances, specifically the signal to interference plus noise ratio performance seen by a typical user. So we assume the location of these interferers are random. So one approach would be, based on our prior work, would be to, for a fixed location, we know how to compute the SINR, and then you repeat this experiment and then average out the results. So that is one of the approaches. But then we also have, with this model, we get closed form expressions, so we can study the system without having to simulate them. We can straight away get the performance. And we characterize the impact of fading, the user density, and also the antenna directivity and gain. The system model is as follows. We consider a network that's of the region is a disk of radius R network here, and the reference receiver Z0 is located at the center of the disk. So ideally this makes sense because you are modeling everything from the viewpoint of the reference receiver. So you put that in the center of the network, and the assumption is that each user has at most one transmitter active at a time. So this assumption is valid if you assume a coordinating hub located on that user somehow ensures that only one transmitter is active in that network. So each user has one active device, and the location of these users, the human bodies, are assumed to be circles in this 2D view, and they are assumed, the location, the center of the circles are assumed to be drawn from a density lambda Poisson point process. Also, since each user has just one interferer, the density of the interferers is also Poisson with density lambda. So the key takeaway here is that we model the blockages as diameter W circles in the 2D network. Now, the signal propagation is as follows. All the wireless link is assumed to have a Nakagami fading. We say that link is line of sight if the line joining the interferer Xi to the reference receiver is intersected by any of these circles shown here, and if at least one circle intersects that line, we say it's blocked and it's non-line of sight. And the path loss exponents assumed are different: alpha L for line of sight and alpha N for non-line of sight. So to simplify things, we just need to look at a region, the shaded region shown here, and if the center of these disks fall in any of these regions, that event causes a blockage for this link from this blue dot. So here this interferer falls in the region, and so it's blocked, whereas in this picture this is not blocked since there are no circles in that region. The antenna model assumed is assumed to have a sectorized gain pattern in the 2D azimuth with main lobe gain of capital G, side lobe gain of small g, and beam width of theta. The reference link is assumed to be line of sight, and it's at a fixed distance and orientation. And we also assume the reference transmitter receive beams are aligned. The reference receiver, Related to the reference receiver, you can characterize the distance to the interferer by the in the complex plane by the angle and the distance, and the relative transmit power from the ith interferer is 0 if it is not at all transmitting. We assume a transmission probability PT. It is capital GT if it's with some probability depending on the beam width of the transmitter. It is small GT otherwise. Similarly, the received power depends on whether or not the interferer lies in the main lobe of the reference receiver and whether or not it is blocked. So alpha I would be alpha L or alpha N based on blockage. Okay, so with this we go into the interference analysis. So the first step that we do is to classify interferers as strong and weak. So for that, first we define the probability that that an interferer at distance r is blocked. So as we can see, that's the probability that there is a blockage in the shaded region, and since we assume it's a homogeneous point process, it's a probability that there is at least one blockage, and we get the expression there. And then with that probability of blockage, which is distance dependent, we evaluate the mean number of interferers that are not blocked. So that would be this is the mean number of these are the mean number of non-blocked interferers. And then we compute a distance our LOS, which we call the equivalent LOS ball, such that the mean number of interferers falling within this ball is the same as the actual mean number of non-block interferers. With this, we say that whenever the distance of the interferer is less than this equivalent LOS ball radius or LOS, the interferer is strong, else the interferer is weak. We classify the interferer based on the distance from the reference receiver. So what this could mean is that given the knowledge of this LOS ball, we could maybe schedule the strong interferers because those are the ones that cause the maximum damage to your system. So that is one of the outcomes or side outcomes of this analysis. So the SINR model is as follows. We have the signal strength sitting on the numerator. We have the interferers falling within this LOS ball, which is the interference from the strong interferers. And then the interference from the weak interferers, we sum them up and take the average of it. We'll see how that would help and also how that is a good approximation. So we have two noise-like terms here. So this two noise-like terms and the actual interference coming from the random locations of the strong interferers within the LOS ball. So this quantity needs to be evaluated, and it turns out to be a simple expression in terms of the actual network size and also the LOS ball radius that we computed, and also the other network parameters, the channel parameters, and the antenna gains and probabilities. So we then add this equivalent average weak interference power to the noise floor. So we have these two, and then we are left with computing the instantaneous SINR, which using standard tools from stochastic geometry, and so it turns out to be like this. So instead of simulating the entire network and then averaging it out, what we have to do is just compute a one-dimensional integral. That's straightforward. You could use MATLAB or Mathematica, and then this is easier than simulating large network and averaging. We also capture the antenna directivity and the user density in this analysis. Okay, so let's quickly jump into the results. First, we look at how the equivalent LOS ball radius varies as we change the network size. So this is important because in most of the work in stochastic geometry, we usually assume an infinite network, whereas here we usually have a finite network for indoor settings. So we look at how the LOS bar varies with the network diameter, network size RNet for different densities. So what we see is that if the network density is high, the value of our LOS quickly saturates, and for it quickly becomes insensitive to the network size. So also in the limiting case, it simplifies to this expression. So what this means is that having a network of, say, size 6 or maybe size 9 doesn't make much difference, because we are going to end up with the same LOS bar radius for these high densities, and anyway we are just going to consider just the interference within this LOS bar. So letting RNet to infinity does make sense for high densities, whereas for lower densities it saturates to the asymptotic gradually, not as fast as for high densities. As for our approximation whether averaging this weak interference is justified, we see that yes, it is justified for, say, when the density is high. So these are the plots obtained from simulations with and without the averaging the non-line of sight interference. So it does make sense and also simplifies things by averaging and adding it to the noise floor. Now this is an interesting plot of the mean number of strong interferers. So these are the mean number of interferers within the LOS bar against the user density for different values of the human user blockage width W. So intuitively and also from the results, you can see that a higher human body width would mean that the LOS bar radius is smaller. So that's why we have decreasing trend with W, because more users are blocked, so the effective number of mean number of strong users is fewer. But then interestingly, what we see is that for all these cases, when you increase the density, you actually decrease the mean number of strong interferers. That's because when you increase the density, you are also making sure that more and more users are closer to you, but they are also blocking more and more users that are standing behind them. So having larger density is actually good in terms of decreasing the strong interferers, and strong interferers are good. Having a fewer number means we need to coordinate with a fewer number of strong interferers, so that makes sense for large densities. So this plot validates our analysis and the simulations. Those are pretty tight. The analytic bond is tight. So we also look at the effect of fading. So M, as you may remember, is the fading parameter, which we assume is the same for both the reference link and the interferer. So a higher Nakagami parameter M results in a better performance, and also so does having a larger blockage parameter W. So some of the conclusions: future wearable communication networks would be heterogeneous. Supporting high data rates in dense crowds is challenging. Especially, it's kind of impossible if you are going for sub 3 gigahertz band, because it would require a lot of coordination and could affect the user experience. Millimeter wave can support high data rates. The analysis done in this work proves that. Does not require coordination between users. The signals can be blocked. That is the reason why it performs better. The non-line of sight interference can be lumped into the thermal noise for calculation, and antenna gain and directional transmission reception hold the key for achieving the gigabits per second data rates. Yep. Hello?
Okay, great, thanks.
Yeah, thanks.